Hello Earth Science students, for today's lesson you're just going to need a piece of paper to take 2 column notes on and a pencil. The title of our lesson today is Pressure Systems. So we're going to discuss the various types of air pressure criteria that can cause weather patterns in both local and global scale. So first let's begin with the term cyclone. Cyclone is a word that you've probably heard in relation to things like tornadoes or hurricanes or big storms like that, and that's because cyclonic conditions can lead to these big kinds of storms. But as far as the definition goes, a cyclone is just a low pressure center. And again, we're talking about air pressure or barometric pressure, so a cyclone is just an area where the pressure is lower than all of the surrounding region. Because of this low pressure center, it generates wind. That blows inward toward the center of the cyclone, because as you recall, wind always blows from areas of high pressure to areas of low pressure, and so if a cyclone is a center of low pressure, wind is going to blow outward towards the inside center of the cyclone. When you have a cyclone, you have air that's rising, because low pressure air rises through the troposphere. As it rises, it cools, mainly by the process of expansion. So as air rises through the troposphere, it gets colder because that parcel of air, it's like a balloon that's expanding bigger and bigger and bigger, and as it expands, it cools down because the particles of air are further apart from each other, so they can't be bumping into each other to transfer heat between them. So when you have cyclones, the weather conditions that are brought on by cyclones or low pressure are clouds, because when you have rising cooling air, you can get cloud formation. Precipitation, because when you have clouds, you can get precipitation. And then also storms. So again, like I said, tornadoes, hurricanes, things like that, those are very strong cyclones or areas of low pressure that can lead to the storm conditions. So now the opposite of a cyclone is called an anticyclone. And a cyclone was a low pressure center, an anticyclone is just a high pressure center. In an anticyclone, the wind is going to blow outward this time, because again, wind blows from areas of high pressure to areas of low pressure. So if you've got high pressure centered in an area, the air is going to flow outward from that center. The opposite air motion, in a high pressure air center anticyclone, air is going to be sinking rather than rising as it does in a cyclone. So as it sinks, it's going to warm, this time by the opposite of expansion, so by compression. So as the air in that parcel of air that's sinking through the troposphere sinks downward, it compresses into a smaller area, and so that creates warmer temperatures. So cyclones and anticyclones rotate different directions based on which hemisphere they're in, either northern or southern, and this has to do with the Coriolis Effect, which we'll discuss further in the global winds lab that we do together in class. So for now, let's just make a quick table. Cyclone, anticyclone. To show the directions that these things rotate. So in the northern hemisphere, where we are, cyclones or low pressure centers will rotate in a counterclockwise direction. And anticyclones do the opposite, so they rotate in a clockwise direction. And then in the southern hemisphere, it's the opposite. So in the southern hemisphere, low pressure centers or cyclones will rotate in a clockwise direction, and anticyclones will rotate in a counterclockwise direction. Again, let's put a little note here that this rotation is caused by the Coriolis Effect. And we'll discuss this further in the lab, but essentially the Coriolis Effect is just phenomenon created by the fact that the Earth is rotating on its axis, and so wind and stuff like that traveling through the air gets kind of deflected one direction or the other depending on which hemisphere that thing is in. Okay, so now let's label these. Let's go ahead and go on the side and label these as local. So these are like small areas of pressure stuff going on that can move. So you can have like a cyclone move into the Helena Valley and then we get clouds and precipitation and stuff like that, or you can have an anticyclone move in and we get clear skies and nice weather associated with an anticyclone. But then there are also global pressure belts that are created by massive areas of rising and sinking air that have to do with convection in the troposphere. So let's move on to work on those now. So we'll skip down a line and we'll begin with the global pressure center that's near the equator. This is called the Equatorial Low. The Equatorial Low pressure center is found at about 0 degrees latitude, which, remember, 0 degrees latitude is the latitude of the equator. So the air here is very hot and very humid because, remember, warm air can have more water vapor in it. So it's very hot because of the direct sunlight angles that hit the Earth at the equator, and it's very humid because that hot air is able to pick up a lot of moisture. When you have low pressure areas, you have air that is rising. And when you have air that is rising, you can get a lot of cloud formation and precipitation and stuff like that. So let's go over here and put, for example, what kind of conditions do you find on the Earth because of the equatorial low pressure system? You can find things like rainforests, like the Amazon. The big Amazon rainforest is because the air is so hot and humid and it's rising and forming clouds. You can get enough precipitation to sustain ecosystems like the rainforests. So next we have the pressure belt called the Subtropical High, which is found at about 30 degrees either north or south latitude. So this is just above the tropics, so that's why it's called subtropical. This air is hot and dry. And the reason that it's dry is because you have a high pressure area, so the air is sinking. And so as the air sinks, it warms by compression, and then as the air warms, condensation can't occur, and so precipitation doesn't occur. Additionally, when the air is flowing around the equatorial low, it's dropping a lot of its moisture as precipitation there. So by the time the air flows to get around 30 degrees north or south latitude, it's dropped a lot of its moisture and doesn't have very much left. So around 30 degrees north or south latitude is where we find the big deserts of the world, such as the Sahara, big sandy desert of Africa. It's found right in that subtropical high pressure zone because the air is so hot and dry. You get big deserts forming there. Next, we have the region called the Subpolar Low, which is found around about 60 degrees north or south latitude. So here in Helena, we're at about 47 degrees north latitude, so we're somewhere in between the subtropical high and the subpolar low pressure belts. So here we have cold air and it's kind of humid. Again, because of the low pressure, you have air that's rising. And as it rises, it cools and it can form the clouds and potential precipitation. So the kind of things that we find in the subpolar low area are called Boreal Forests, such as like the taiga of Russia. It's just a really big like pine forest, and so you can find forests that aren't as lush as the tropical rainforests at the equator, but still large forests because there's enough precipitation to sustain the plant growth there. Finally, we have the polar high pressure belt. So this is found right near the poles, which the latitude degrees of the poles are 90. So 90 degrees north or south latitude, North Pole or South Pole. Since it's high pressure, it's going to be rising, and we have very cold, very dry air here. And again, the air sinks because of the high pressure. So you don't get very much precipitation. So even though it's cold up there, it still is kind of considered to be a desert because there's not that much precipitation. So for example, near the polar high is where we find features like the tundra, which is kind of like a frozen wasteland with not a lot of trees or plant growth, and then also areas of permafrost where the moisture in the ground is all permanently frozen because the temperature never gets high enough to melt the ice that is inside of the ground. So let's just put an important point down here, that you've got all of these pressure belts throughout the different latitudes of the Earth, and the air is constantly kind of circulating between these things, and this causes the general temperature of the Earth to be kind of balanced so that it's not really cold near the poles and really hot near the equator. So we'll just say airflow between the pressure zones moves warm air from the equator toward the poles, and vice versa, cold from the poles in the direction toward the equator. So this causes the balancing of overall global temperatures. So again, if we didn't have this, we would have really, really cold poles, really, really hot equators, but since we have this kind of global airflow caused by these pressure zones, we get a balance of the temperature globally, which makes it much more conducive to humans living on the Earth.